So good afternoon, everybody. I'm very pleased to have you here to host you and greet you here at this PHIDIAS webinar this afternoon. This is actually the last webinar of the series on the use cases of the PHIDIAS project, bridging the gap to facilitate selection and image analysis for the surface monitoring. So I'm Francesco Zimanti. I'm a project manager. I work for Trusted Services, an Italian SME, and I'm very honored to be the main leader of the communication and dissemination strategy of the PHIDIAS project. Just give me a couple of minutes to contextualize the nature of the event. So I'm pretty confident that most of you that are here today are already well familiar and knowledgeable about what PHIDIAS is. PHIDIAS is an European Commission funded project under the framework of INEA and Connection European Facility scheme. We have started back in September 2019, so we are crossing now the halfway line of the project. PHIDIAS is made of 13 different organization research institute spread all over Europe, coming from 5 different countries, and led by CNES. CNES is the French National Computing Center for Higher Education. You can see in here the main objective, the main goals that are in pursuit of from PHIDIAS. I would like to, in a very nutshell, say that the core essence of the project relies in the development of 3 different use cases that aims at the development of data post-processing methods coupled with HPC capabilities, which will be deployed as a service for several end users. Among these end users, we have, of course, the scientific community and the research landscape. We have the public authorities, some private sector players, but also the citizen scientists. What PHIDIAS is going to do in these 3 years is the development of 3 different use cases. The first one is the intelligent screening of satellite data. There is a second one entirely based on ocean and the development of cloud services for marine data management. And the third one revolves around big data and Earth observation. That is actually the crux of the matter is the subject matter of today's webinar. As you can see here, and as I said at the very beginning of my speech, this is the 3rd webinar of a series where we have tried to showcase the main outputs and the future trajectory that all of these 3 use cases wants to walk through across the lifespan of the PHIDIAS project. So during this webinar today, we're going to showcase how PHIDIAS can be a real chance, a concrete and tangible opportunity for the scientific community on the whole, of course, but specifically for land managers and agricultural players to take full advantage of HPC architecture in order to facilitate selection and image analysis activities for land surface monitoring. So the 4 esteemed speakers that are concretely working and successfully working on the project in this month are going to feature a few examples and case studies to present the approach that is going to industrialize the processing chain in order to carry it within the HPC environment. So I'm going to cut to the chase and leave the floor to the most competent one. And I just wanted to give you an overview of the main points that we are going to tackle today, and the squad of panelists that we have. So we have the first speaker is Jean-Christophe Desconnet, that comes from the Institute of Research for Development in France. That is the main developer and the main responsible one of the use cases too of PHIDIAS. Following, we will have Mr. Cyprien Alexander, still from IRD, and we will have as guest of honors Mr. Gérald Fenoy and Dorian Ginan, respectively from GeoLabs and GeoMatisse. They provide a concrete and technical support to the successful development of the use cases. So I'm done with my introduction. Just a bit of a housekeeping before moving forward. I'm here today with my dear colleague Julie Arteza and Valeria Andreoli. That will interact with you in order to provide you further and more meaningful information on the project. So you will hear from them in the chat. And speaking about that, I want to remind you the possibility throughout the whole duration of the event to, if you have any curiosity, any question you want to pose to the speakers, just seize this chance and use the Q&A anytime, the Q&A box at the bottom bar of your screen to drop your questions. So the speaker will be more than pleased to get back to you and provide you an exhaustive response. In the end, we will have the possibility, if we need it, to have a Q&A session to address the most important questions. So it's time to me to stop and to shift and to leave the floor to the first speaker, that is Jean-Christophe. Jean-Christophe, the floor is yours, and you can take anytime the floor.
Okay, thank you very much, Francesco. Hi, everybody. I share my screen. Do you see my screen in full screen or not?
It's about to come. No,
it's okay.
You are not in full size screen yet. We can see your slide, but
okay. Another try. It's okay.
Almost there. Yeah, now we're there.
Great.
Praise God.
Thank you very much, Francesco. Hi, everybody. Well, my presentation is the first one is more or less to set the scene, to give the floor to the other. I want to give some key element to understand what the meaning of the work that we done in the WP5 called Big Earth Data for environmental monitoring. The idea is to, in other words, is to reach the challenge about availability of processing surface quality is a challenge that we want to reach with the WP5 in general in PHIDIAS project. First of all, it's very important to say that since various years and decades, we know that the remote sensing images are underused by the target user, and I put on the slide the different one. The target user are a researcher from a remote sensing specialist, but other from health, from hydrology, from climatology, or something like that. They are also remote sensing is important for government agency, which monitor the territories, land surface. It's also important for the land manager, agriculture manager, something like that. That we want to note to say in this slide that it's very hard way to use land remote sensing images because there are many bottlenecks, many barriers, like accessing to the relevant images, getting appropriate equipment to store and to process the images, also to have skills to do that. It's okay. I heard something. Okay, great. Alors, why the first barrier is the barrier is an opportunity also. That's since many years there are very large panel amount of image coming from the space. I put on the right the images of the ESA mission, but there are other national or international agency which launch many satellites. And today the difficulty for the user is to find the relevant images according to the spectral or spatial and temporal resolution that the images give. And it's really a link to the the needs that are their needs. So it's interesting. It's real crucial to say that today it's very difficult to access and to discover the right images. And one of our objective is to reverse the paradigm, bring the data to the user, and go ahead to the to deploy and to implement the paradigm, bring to the user to the data. And I hope that we go ahead about that. Next slide. One of the first steps to break the bottleneck is, you understand, it's first of all to access to the right data, and we put with the various projects in the land surface community in French, particularly, we build a data portal which propose in interoperable manner the access to very high resolution data, like in the GeoSuite project, which propose through a license, a free license, to spread out the access to the large number of users and research user, but also publicator. In the right side of my slide, there's also a big, interesting, very relevant project is the PEPS platform, which provide access to the Sentinel-1 and 2 images in free access, of course. This is a French hub of the Sentinel product provided by the CNES. But it's not sufficient to provide access and discover right discovering of the images. Is also necessary to produce a new knowledge with images. It requires many things and many conditions, technical and scientific conditions, to have the facility to manage the data, to analyze it, to classify the images. It's also complicated to have sufficient storage and processing resources to process the data. And finally, it's also very important, more important, critical, to set up and maintain a stable and operational environment to process the data in a reproducible manner. It's really a thing. This is really critical. In this way, to address this challenge, the scientific remote sensing community was organized since a few years around the Land Data Surface Center called TIA. And TIA is also a collaborative network called Scientific Expertise Center, or in French, Centre d'Expertise Scientifique. The purpose of this network is to work around the 10 themes. It's a network of remote sensing specialists. It is to work around the 10 themes: agriculture, forest, urban, coastline, health, water, and something like that, and to provide some algorithm and some scientific data processing, taking advantage of the different Sentinel images, spot images, and something like that, and to prototype who give some proof of concept to map land cover. For example, in the left side of my slide, land cover IOTA chain is a large non-output of this network. Also, some mature with the right spatial resolution. There are also some algorithm products around the health environmental purpose, for example. But I try to, okay. But for us, is not enough. There is really a gap between the output coming from the scientific data processing community, from the remote sensing specialists, to give available this kind of processing chain and the products coming from this processing chain to have accessible, scalable, and reproducible data processing from the end user. Donc I talk before the end user, the other researchers, the government agency, or the land manager, for instance. And really, for us to fill the gap between the academic production, which is our the output are has a different level of maturity in terms of technical readiness level, to the needs in operational manner. So one of the objectives of the WP5 is to reach this gap and propose, define and propose a data model, protocol, and tools to deploy and link end user analysis and discovery environment with execution environment on the HPC center. And I try to represent in this slide this more or less this approach and the overview of our work on the WP5. On the left side of the schema, we have more or less the execution environment that we want to set up, including the putting the data processing chain in an operational manner close to the HPC data center. On the right side, there is the different environment for the end user, including discovering facility and analyzing facility, providing environment like a notebook to analyze and make data science on the data. In the middle of my schema, this is the link between these two worlds, the world of the user, the world of the web processing services server. This is a way to link the two worlds, and also the next presentation will give more precise element about these three compartments. Okay, thank you. I finished my presentation. Thank you very much.
Thanks a lot, Jean-Christophe. It was very insightful. And I'd move now to Cyprien for the next presentation. I would like to remind you that we saved a space for the very end of the webinar, like 5 up to 10 minutes, in case you should have any further question that might be tackled. And of course, feel free to drop the question in the Q&A box at the bottom of the screen. So Cyprien, it's your turn now. You can take the floor, share your screen. That is already perfect and visible, and just go for it. The floor is yours. Thank you. But you are muted, Cyprien. You have to restart.
Sorry.
Now it's okay. Now it's okay.
Okay, thank you. So hello everyone. I will present to you how it works on how to go from processing chains prototyping to HPC-based on-demand services with the particular practical example of soil moisture service. I said before, the main idea of our work is how to allow simplified access to high-performance computing for researchers and non-researchers users. The underlying question is how to turn processing chains developed by the researcher himself to fit his problematic into an on-demand service based on HPC and accessible by different kinds of users. In that, what are the engineering issues for developing such as processing chain? And once the processing chain is functional on HPC, how to allow the access to the computing capacities for these users. I will first quickly present to you the soil moisture service processing chain. It was created with the HPDA soil humidity at high spatial resolution under the direction of Nicolas Baghdadi and developed by Loïc Lozac. The code is accessible at the Loïc's GitLab. The heart of the chain is an algorithm using model inversion to retrieve the soil moisture value from Sentinel-1 SAR images at the plot scale. The chain also uses plot vector files, DEM, and NDVI from Sentinel-2 images. And the NDVI is used to adjust the impact of vegetation on the moisture estimation. To go into more detail, the chain uses data from different providers. For example, Sentinel-1 images are from CNES, Sentinel-2 images from TEIA or CNES, depends on the localization of the study area. The GEM, SRTM are from the ESA, and the plots in vector format are from the official inventory for France and from users for other locations. One of the benefits of the chain is that it can deal with different data sources and large amount of data. It is really transparent for the user because they only need two input parameters, the date and the Sentinel-2 tile ID as the study area. The chain produces to the inversion model a soil moisture map in raster format or CSV and soon in shapefile. We've got two ways to produce the soil moisture service. First, a systematic production with a frequency of 6 days on some countries. And for other countries, an on-demand processing is available. In terms of technology, it's all developed in Python and use GDAL and OTB and TensorFlow, a neuronal network, for the model inversion. Now the question is how to push it on the HPC in the way to execute it. So the solution is containerization. It's an encapsulation method that allows to create a runnable image of the application with a complete environment and all these dependencies. For example, you can run the soil moisture service without Python installed on your computer because all is in the container. That's not a specificity of the HPC development, but it's particularly adapted for the HPC. It's a standardized method to store and execute application. In this sense, it's really easily deployable. We've got no compatibility issues between hosted applications. For example, if you have two applications using two versions of the same library, by containerizing each application, you will isolate the environment and so exclude any conflict between different library versions. Two solutions are known for that, Docker and Singularity. Docker is largely used in the programming community. It's a simple way to share programs between common users, but it got some security vulnerabilities, especially for access right management. In the other hand, we've got Singularity. It's an open source solution, but specially developed for HPC. So it's particularly suitable for our use. And the little extra is that you can run Docker images. I spoke of security before. It's a common thread when developing in HPC. So we have to adapt the processing chain to fit the security rules. For example, the fact is that we can't download our data through computing nodes on HPC. We deal with large amount of data. For example, for 15 days on France Maiden, we need 3 tera of Sentinel-2, more than 300 gigs of S1, and almost 600 gigs of GEM. So for that, we've got 3 solutions. First, the data storing. It's the simplest way, but the size of the data is a limitation factor. The second solution is an on-demand download. For that, we execute a part of the processing chain on the front HPC machine. That's not the fastest method. And the third solution is file system virtualization. We use iRods. It's a solution among others. But by this way, we can create a direct link between HPC and data providers. And using metadata links, we can transfer quickly the data for processing. So we choose the first one, the data storing for the SRTM, because it's a low and finite amount of data. And for Sentinel images, we'll use the on-demand download for the moment and migrate to iRods in the long term. This issue can be encountered in different stages of the development because of the complex organization of the HPC architecture. For example, for specific data access protocol, storage, or access right administration, etc. So once the processing chain is functional on HPC, how to allow the access to the computing capacities for the users? We have to create an interface between users and container. But the fact is that we have a heterogeneous community, users non-familiar with code in one end, and in the other end, users more familiar with code and want to go further in the product analysis. For that, we choose different ways to access computing capacities. First, a standard web user interface, as we can see in the GeoSuite portal, that allow to select already processed products or order new products. If the user wants to go further in the data analysis, he can access to the Jupyter notebook to run commands on selected products. This part will be described by Dorian Chinan from Geomatis later. Between our interface and HPC, we need a processing orchestrator, a zoo kernel. It uses the web processing service protocol. It's a standard from the Open Geospatial Consortium and defines how a client can request execution of a process and how the output from the process is handled. This point will be dealt by Gérald Fenoy from the lab later. So to conclude, as we've seen, making an HPC capacities accessible to a wide public implies taking into account several parameters at different levels. Some at the processing chain level with containerization, for example. Others at the HPC level to feed the security rules and HPC architecture. And last, at the user interface level. As you know, in the context of open science, all these developments are made by respecting as much as possible a fair logic, as the code, method, and data have to be findable, accessible, interoperable, and reusable. For that, we are using standardized applications and protocols, Python, Singularity, WPS. And one of the objectives this year is also to make a link with work package number 3 of PHIDIAS, which is in charge of metadata continuity. And last point, this work done on this processing chain has given us the opportunity to learn about the method and the industrialization process in order to bring other algorithms on HPC more easily. So thank you.
So thank you, Cyprian. It's a very, very nice and overarching presentation. I appreciate a lot the final remark on the common thread of fair data, because the fairization of data is one of the key elements of the PHIDIAS project. So it's nice that you brought that up, and even an interlinkage between the different work packages. That it shows how the project doesn't work in a silos, and all the effort are pretty much interconnected. So I think we can move on, keep connecting the dots, and I think it's Gerald's turn now. So when if you're ready, when you're ready, Gerald, you can take the floor. Yep. Hello.
How should I stop the screen sharing?
Yeah, take your time.
Sorry.
It's coming. Don't worry.
It's good.
It's perfect. Floor is yours.
Thank you very much. So good afternoon, everybody. I'm Gérald Fenoy, CEO from GeoLabs, and I will present to you shortly how we implemented online and on-demand processing of satellite images by using WPS services and what we call the missing link in the chain, and as was presented by both Jean-Christophe and Cyprien. So first of all, I will introduce you what is the main goal of the main objective of the project on our side. So as Cyprien told, we have an interface that will use HTTP and XML encoding to communicate with various web services like catalog web services or WPS server to access processing resources that will be made available on HPC server as singularity images, what you can see on the right hand side of the schema. So you also notice on this slide that I have distinguished in between data diffusion from application diffusion, because indeed we have one big part that was presented earlier and which can be seen as a bottleneck, which is the data diffusion. But we are mainly focused on our side on application diffusion, how to share the know-how from scientists to, let's say, basic users. On this slide, you also see that WPS server named Zoo project, actually the Zoo kernel only, is also able to automatically output results as OGC web services like WMS, WFS, WCS by using the GIS engine named map server. So first of all, I may briefly introduce what is processing services, web processing services about. So we are commonly using application that I called logged-in applications. When you have the client and the server that are the only one to talk the same languages, so they are strongly linked together, which is first picture on the top of my slide. It was already presented by Cyprien, but the Open Geospatial Consortium, which is a well-known international consortium, specifically publishing a web standard for very broad kind of web services and from data to application sharing. So here we are, I speak about web processing services. We got two versions, one version that has been published in 2007 and the other one in 2011. So the WPS, as Cyprien introduced, give generic interfaces. So it let people create multiple server implementation and also multiple client implementation. So the client implementation, like you can see on the bottom right side, you can see multiple applications that can be run on server and communicate with other server. You can have also servers that are communicating between each other. And you can also have the same kind of client application that is running directly on your desktop. Obviously, it also permits to have automatic capability addition. It means that once you have a WPS client application, it can discover on its own the new services that are available and produce the HTML form or any kind of form to input the data. And it also ensures the reproducibility of execution because there is an internal mechanism to handle history of execution. So you can rerun the same execution again. So for web processing service, we have mainly, I say only mainly, 3 main request type. So we have the get capability when a user asks himself, what is services that are available on the server? So he will simply ask for get capability and will get the available service list. It is like when you go in a kebab place and you want the cooker to prepare a special kebab. So first of all, you ask for the menu. Once you have the menu, you have all the different options with the described process, providing the information of a detailed description of service, including parameters and outputs, formats and everything. So from the menu, you can decide if the kind of meat you want to have, the kind of vegetable you want to have, if you want a bread or not. And then once you are ready to pass your order, you can run the execute, which can be run synchronously, meaning that you can stay at the kebab stand and wait for the cooker to give you the kebab ready. Or you can also order from home and get it delivered for future use. Okay. So this is the analogy I am making with WPS 1 and 2 version. So once, actually, I was speaking only about web processing services, and we have nowadays a new coming API, which is arriving from the OGC. I will speak about a bit on the next slide. So we have the Open API, which become very famous since 2017 by the fact that the Linux Foundation sponsored the Open API initiative. It was initially named Swagger specification, and it is a new way to define REST contract by using a different syntax, which is more lightweight than the XML we were using in WPS, which is based on JSON and YML. One good point also about this new Open API is that from the Open API definition, you can produce automatically both documentation, client code, or server code automatically. So the OGC that I was speaking about earlier realized in 2016 that their web services standard were Web API. So you have on the right side the currently ongoing work about this Open API with feature, and we will be mainly speaking about the processes, the OGC API processes. So on the technical point of view, we have developed the Zuzu project, which is an open source software server implementation of the OGC WPS standard. So it is composed of multiple parts, but I won't go in deep details. So on the left-hand side, you have the user, which is connected by to a web application, let's say, which will have some client code to interact with WPS or OGC API processes through HTTP method. He will communicate with the Zoo kernel. The Zoo kernel is a lower level engine that is responsible to execute services. So at the inception of the project, we were thinking that the Zoo kernel should be able to reuse and execute any kind of code. It can be like you can see on the slide, you have GIDAL, you have GeoTools, you have GEOS, and you have R. But you may say that GeoTools and GIDAL are implemented in using different languages, and R is a language in itself. So GIDAL is a C, GeoTools is a Java library, and R is another language. And just to mention that the Zoo kernel is able to handle any kind of programming language and run it as a service. After this, we realized that it is still requiring some work to handle all these libraries and make them available to the end users. So we focused on Orfeo Toolbox and Saga.js processing engine and automate the publication of all their application as WPS services, and nowadays as OGC API processes. Also, we have provided a Zoo API, which is highly flexible. You can build up new services by combining multiple services that can be written, like in this example, in multiple programming languages, simply by using JavaScript on the server side. Last but not least, with GeoSuite project, we also implemented the HPC support, the HPC service support, which means that you only have a configuration file, and the Zoo kernel will be able to automate the execution of service, to schedule execution of service on the HPC by using Slurm and SSH. So with the OGC API processes, I just show you quickly Redux documentation on the left-hand side that has been automatically produced from the OpenAPI specification published by the Zoo kernel. And on the right-hand side, you have a Swagger UI basic client, which means that a new web developer can come and directly interact with and run a request live directly by using this Swagger UI basic client, which you don't have to implement anything. You just have to give the URL to your API, and the Swagger UI will show up and give you all the opportunity to execute request. So with the remote service execution in the GeoSuite project, we were using WPS2 for some specific reason, like additional parameter for filtering access to imagery. So in the GeoSuite project, you have the Zoo kernel, which is communicating with Slurm with SSH and SFTP to upload the data. We are using asynchronous callbacks invocation for execution history recording. Actually, I mentioned that because in the OpenAPI, we have the callback and we reuse the exact same code to get up-to-date status information when running, when executing a service. You have automatic publication of the execution history, as I told you earlier, both, but in this case, in this specific case, in the GeoSuite project, both inputs and outputs were published through OGC web services. As I said earlier, we use SSH and Slurm for remote execution scheduling. And unfortunately, we were relying on mail that should be from the HPC server. So in this PHIDIAS project, our goal is to switch from a monolithic view when we have only a single Zoo kernel to a containerized view, where Zoo kernel, when we split the Zoo kernel in between multiple instances. So we will have mainly the client on the left-hand side that will still interact using HTTP to the Zoo kernel that I named request handler. This request handler will communicate by using advanced message queuing protocol, using RabbitMQ, implemented in RabbitMQ. It will send messages, and the Zoo kernel that I named process manager will handle the request, will really handle the request. For doing so, we will rely on a PostgreSQL database like we did in GeoSuite, and we will use Redis mainly to give back information by using WebSockets to the client side to get up-to-date status of execution. So to conclude my presentation, as I try to explain, even if it was a short time, WPS is facilitating the diffusion of scientific knowledge by defining a protocol to discover, access to, interact, and reproduce service execution. So this is a fair definition. In the addition of the OpenAPI support through the OGC API processes, which is undergoing, it is also the diffusion of knowledge of scientists by providing this time out-of-the-box tool to document, discover, access to, and interact with, and reproduce service execution. Why I made this distinction is because on the second line with OGC API processes, I say out of the box. It means that you don't have to write one line of code to get it up and running. Also, by using containerization, we reduce the additional development. using OpenAPI, we reduce the additional development. As I told you, we have out-of-the-box tool to produce Python code or any web client. So we can reuse this information, this code produced within Notebook. We ensure scalability by using advanced messaging queuing protocol. We ease maintenance and deployment by using the containerization. And history management will be used to produce provenance metadata of the resulting product. This is all for me. Sorry if I was long. Oh no, it's good. Fair enough. Okay.
No, it was very good, Gerald, and thank you too for your very overarching and very detailed explanation of the Zoo project. So I think we can keep up pace. Zoo project, I have to say, my personal opinion, they have a wonderful branding as well. It was really,
Thank you.
Yeah, congratulations. It's really fancy. So we are pretty much in time. It's time now for the last presentation. So I'll leave the floor to Dorian. Whenever you're ready, you can pick it up and you can start sharing your screen and your slide deck presentation. And
I'm quite ready. Okay, it should be good. Can you see my screen? It's okay.
It is now perfectly good, and floor is yours, Dorian.
Okay, fine. Okay, so hello everybody. I am Dorian Ginan from Geomatis. Geomatis is a French SME specialized on spatial processing data, on spatial data processing. And for the PHIDIAS project, we are working on deploying a solution that will help user and also data scientists to access to a big amount of data. It is the part that the user will see, and it will use all the other components and infrastructure that the other speaker just talked about before. So I will mostly focus on the user point of view. Often, the user doesn't need to access to a collection of dataset, but rather want to directly access to a result for this dataset for a specific spatio-temporal area. It's as talked about Jean-Christophe, it's moving from bringing the data to the user computer and rather bring the user to the data. It's the same idea. And due to the volume of raw data that are accessible, it's not very easy to process all the data available in advance. It means we want to be able to process the data when a user asks for, and it's near from the analyze ready data approach that other geospatial community are designing now. Okay, so what we did in PHIDIAS is that we define a product that we call a virtual product. It is an arbitrary aggregation of raw data that user can manipulate as a unique data cube. For example, it can be an optical layer that mix two different images from satellites, or temperature product that is also mixing different temperature coming from different satellites. And to that we use the examine Datacube solution to access to this product and to manipulate some subsample of this big data cube, depending what the user wants to do with. So how it's work? Basically, the first step is to create a big indexes for all the data that are stored, all the raw data, the raw data sets, the files, or whatever, let's say the image, the raw image that are stored on the data lake. And we will define and express the overall geographic extent, the overall time range of all the images that are inside the product, the native resolution, the unit of measurement, the min and max value, and this index we are creating and we are refreshing each time a new data arrive on the system will allow to find very fast the data set that are included in the user query. Then we can provide to the user no more the data as in the same format that they were stored on the data lake, but in the way the user wants. I say user, but it could also be a software. It means, for example, that we can provide, depending which languages user or software want to use, we can provide a NumPy XArray structure, a Java object structure, a Dask if we want to parallelize the process, and we will provide the data at the good resolution for the user with the good coordinate reference system, and in at the format, the export format you want, if you want to have a format. And then doing that, we can use the Datacube and the raw data with other library, for example, Author Toolbox, Scikit, or other Python ecosystem. And it could be useful for in a data scientist for data scientist user. But the virtual product can also be used as a classical product in the geospatial infrastructure. For example, it will be available in the catalog, and you can ask for downloading the data as any other of data that is on the PHIDIAS data lake, or you can see the product as a classical web map service layer, and browse through the spatio-temporal dimension of the data. But you can also access directly the Datacube through a notebook. Well, I don't know if everybody know what is notebook, but it's an easy way for data scientists to create and collaborate toward the conception of new algorithm, or to create new data analysis. And as talked Gerard just before, we can also, through this interface, use the process that has been designed and shared through the WPS Zoo kernel interface. So to conclude, I have a short video. Okay, let's see. Okay. So here is just an illustration of what we can do with virtual projects. So the first step is to define what you want. So here you can see I want to have a Datacube compound by Sentinel-2 product between these two dates. It will provide a cube of data, and here you can see the metadata. It means how it's compound the cube you receive. It is expressed in a standardized WKT format, and you can then know, okay, the projection I receive is this one, the geometry of my cube is this one, and in this cube I have the following dimension available with, if we have some description of the dimension, and the min and max value of the cube. Knowing that, data scientists will be able to better design and easily design a new data analysis or a new algorithm with this kind of description. So here is the second cube, but here we are asking for a specific resampling operation because we do not want to use the native resolution, but a specific resolution. And then you can see that we will use an OTB of a toolbox functionality, and for example launch, calculate an NDVI or land surface classification for the specific data cube. It is one possible use of the virtual product, but as I said before, it can also be used to launch process on demand, and this process on demand can be shared in a catalog as if it was an already existing data. So the overall idea by working with virtual product concept is to mask to the user all the plumbery of and the complexity of the system, and to provide him easy way to access the data, to bridging the gap between very big data infrastructure and user needs. So it's finished for me. Thank you.
Thank you very much, Dorian. Thank you very much. So we have very rapidly come to an end to this hour together. I think it's it's now time to wrap up. But before wrapping up in a very quick way, I would like to leave just a couple of minutes to Jean-Christophe. I think I would like him to give a super quick explanation of the future trajectory of PHIDIAS and what has to be expected in terms of technical advancement in the coming 18 months, let's say, from here to the end of the project. So I would like to give the floor to you again for a couple of minutes, Jean-Christophe, if you want.
Thank you, Francesco. Thank you, everyone, to hear us about mainly technical aspect of our work on the WP5. But as you understand, I hope it's crucial for us to provide such architecture and element to bring the user to the data and not the reverse, as we said at the introduction. And for that, PHIDIAS is really a great opportunity to go to this kind of architecture and kind of service for the for the academic sector, but also it's very important to the private and to the society. It's very important. I think the PHIDIAS project and over the PHIDIAS project, the EOSC initiative, European Open Science Cloud, is really a great opportunity to open the academic output like chain, but also data. And we are really in mind that in PHIDIAS we should first of all provide open source, but also open source component to build the EOSC, the research web of data, in using and implementing the FAIR principle to do that, of course. And also, it's very important, this is a condition to do that. It's very important, this is the case of PHIDIAS project, one of the objectives of PHIDIAS project is very important to open the HPC center to maintain operationally this kind of approach for the academic community to the end user and society and private sector. This is my word of conclusion. And we hope that we have a success to do that in the next months. We are today at the middle, more or less, of the PHIDIAS project. Thank you very much for all of us.
Yeah, thanks a lot to you, Jean-Christophe. I want to personally thank all the ones that joined us today here this afternoon for this webinar together. It's been a pleasure, and of course, our esteemed speakers and their great work that have put up to run this successful webinar. And we are going to conclude with this event our series on the use cases that started in the past summertime. And so we wanted to give you a walk through our main use cases. Now we came to an end. This doesn't, of course, mean that PHIDIAS related events will end today. So I would warmly invite you to stay tuned with to our social media, to our main channels. There is a lot to do for the project, as Jean-Christophe said, in the coming 18 months. And yeah, we will be pleased to join with you again for other events in the coming months. So stay well, and thank you for being here today. And we'll see you soon. Take care. Thanks again.
Goodbye.